Okay, so we are ready to define the class NP. We'll first do this using an example. Okay, so the example, we'll pick a problem. The problem we pick is HC. Okay, the input is a graph G, and the question is, does G have a Hamiltonian cycle? Okay, so this is the question. Now, forget algorithms for the time being. Okay, so we are not going to discuss algorithms. What we are going to do is discuss a game between two players. Okay, there are two players. Okay, we'll call them prover and the verifier. You'll see why they are called prover and verifier very shortly. Okay, this prover, think of him as all powerful. Okay, he knows all answers that he's supposed to know, and even answers he's not supposed to know. The verifier has limited resources. In particular, he doesn't have too much time. Okay, limited resources. This includes time. Okay, now the prover and the verifier meet. Okay, they are sitting in a room, and they see a graph in front of them. Okay, now the prover looks at the graph and says, this graph is a Hamiltonian cycle. The verifier, who's a bit mistrustful of the prover, asks him why. Why does the graph have a Hamiltonian cycle? Now, the prover can convince the verifier that the graph does have a Hamiltonian cycle very easily. And how does he do it? He just gives the edges in the graph which form a Hamiltonian cycle. Okay, so he picks any Hamiltonian cycle in this graph, and he tells the prover, he tells the verifier, look at these edges. These edges in the graph form a Hamiltonian cycle. The verifier, even though he's sort of limited in resources, this much he can do. Given a Hamiltonian cycle in a graph, he can verify that these edges in fact do form a Hamiltonian cycle. Okay, so let me just write this conversation between the prover and verifier down. So the prover says yes. So this yes is an answer to this question above. Okay, the yes here is an answer to the question, does G have a Hamiltonian cycle? The prover says yes, the graph has a Hamiltonian cycle. Okay, there is an input graph that both of these are looking at, both the prover and the verifier are looking at. The prover says yes, the graph has a Hamiltonian cycle. Okay, the verifier then asks why, and the prover supplies edges in some HC in G. Okay, and the verifier verifies that these edges indeed form a Hamiltonian cycle. Okay, so this is the conversation. Let's go over it again. The prover says yes to this question. Okay, and to supplement his statement, he supplies the edges in some Hamiltonian cycle in G, and the verifier looks at these edges in the Hamiltonian cycle, and it's easy for him to verify now that these edges indeed do form a Hamiltonian cycle. Okay, yeah, so this is the game that we will sort of consider, and in some ways we have already proved. I have not defined what an NP is, but we have actually proved that the Hamiltonian cycle problem is in the class NP. Okay, So let's formally define the class NP, okay, and then we'll see why this constitutes a proof that Hamiltonian cycle is an NP. So Hamiltonian cycle problem, of course, is a decision problem. The question we ask is, does there exist a Hamiltonian cycle or not? It's to be answered yes or no, so it is a decision problem. Okay. So a decision problem, here's the definition. A decision problem is said to be in the class NP if for all yes inputs. Okay, let me write this down, then I'll explain what this means. If for all yes inputs there is a proof, okay, you can think of this as a advice or a string. Okay, so this is, think of this as the string that the prover gives to the verifier. Okay, so this advice or string is what the prover will give to the verifier. So there is a proof using which it can be verified quickly that the input is indeed a yes input. Okay, so let's now look at this. Okay, there are some terms that I need to describe. First thing is, what is this yes input? Okay, what is quickly? And then what does the statement mean? Okay, so let's focus on yes input. See, this problem is a decision problem. Okay, so since it's a decision problem, for each input the answer is either yes or no, right? So yes inputs are those inputs for which the answer is yes. Okay, so we look at only those inputs for which the answer is yes, and we say that for these inputs, I do not worry about what happens to the no inputs. Okay, for the yes inputs there is a proof, which this is the proof that the prover gives the verifier. Okay, so what's the proof? So this proof, so yes input, it's sort of yes inputs are inputs for which the answer is yes. Okay, this is one. The proof is what the prover sends to the verifier. Okay, and quickly means in time polynomial in the input size. So I could have said efficiently, I guess that's what I've been using, but quickly, efficiently, okay, they all mean the same thing, which is that it can be verified in time polynomial in the input size. Okay. So let's go over this definition again, since it's sort of important. Okay, so let's go over this definition again. A decision problem is said to be in NP. Okay, if for all yes inputs there is a proof. Okay, there is a proof using which it can be verified that the input is indeed a yes input. Okay, so let's look at our previous example. For Hamiltonian circuit, if for all yes inputs, okay, for a yes input, which means if the graph does have a Hamiltonian cycle, there is a proof that the prover can give the verifier, using which, okay, this proof consists of edges in some Hamiltonian cycle, and using this the verifier can easily verify, okay, in polynomial time whether the graph has a Hamiltonian circuit or not. Okay, so this actually proves that Hamiltonian circuit, the problem Hamiltonian circuit, is in the class NP. So let me highlight the main sort of points in the definition. Okay, and then we will go over this again. So first, it has to be a decision problem. Okay, so answer has to be yes or no. We look at only yes inputs. Okay, and on yes inputs, supply a proof. This proof should help the verifier verify that it's a yes input. Okay, which helps verification, and this verification has to be in polynomial time. Okay, so these are the crucial things. It has to be a decision problem. We only look at yes inputs. It's only for yes inputs that the prover has to convince the verifier, and to convince, he can give a proof which can help with the verification. Okay, so here is let me sort of draw this diagrammatically. So here are the here is the yes input. So you pick any one of those yes inputs. The prover is looking at this. Okay, so is the verifier. Okay, and the prover sends a proof or an advice, sometimes called an advice. It's just some string. Okay, you can think of it as a string of zeros and ones, whichever way the verifier looks at the string and sort of figures out what the prover means. Okay. So on yes inputs, the prover can send some proof to the verifier, using which the verifier in polynomial time can verify that in fact this is a yes input. Okay, so let's do one more example. Okay, this example is of composites. So the input is a positive integer L, and the question is L composite. Okay, this is the question. Okay, so we want to know whether composites, this problem composites, is in NP or not. First thing, it is a decision problem. Okay, so we can, it's a problem that we can look at which could be in NP. Okay, so the first thing it has to satisfy, that the first property it has to satisfy is that it must be a decision problem, which it is. Okay, the question asks if L is composite, and the answer is either yes or no. Okay, what's the next thing? For all yes inputs, okay, there must be some way for the prover to convince the verifier that in fact it is a composite number. Okay, so let's just do this. So we are looking at yes inputs, which means L is composite. So what is the proof that the prover can give the verifier? Okay, so well, I guess it must be sort of obvious by now that if you know that something is composite and you want to convince somebody that it is composite, you can just give the two factors. Okay, so you give So the proof that the prover supplies to the verifier is a factorization. Okay, so so he gives, let's say, L1 and L2. So this is the factorization of L. So the verifier checks that indeed L equals L1 times L2, and neither of these is 1. Okay, L1 and L2 cannot be 1. So this proves that this is a proof that the prover can give to the verifier to convince him that some number is composite. So one question, I guess, which most people sort of encounter when this definition is made is, you focus only on the yes inputs. So what about the no inputs? Okay. So take composites for the time being. Okay. Input is a positive integer L. Question is L composite? Let's say the answer is no. Okay. The prover says no, it's not composite. Now, how can he convince the verifier that it is not composite? Which means he has to somehow convince the verifier that it's prime, that the only sort of numbers between 1 and the number that divides it are 1 and the number itself. There's nothing else in between. Well, if you think about this doesn't seem to be as easy. Okay. Actually, in this case, there is a way to do it. Okay, but the ways to do this, it's certainly not easy. Okay, there's a recent result which says that even without an advice, one can figure out whether a number is prime, but that is way beyond the syllabus for this course. Okay, so let's again do this for the Hamiltonian cycle problem also, just to get a hang of this. Okay. Here. Now, when the answer was yes, the graph has a Hamiltonian circuit, there was this proof can be supplied, right? Edges in some Hamiltonian circuit in G. Supposing the prover had said no. Okay, if you look at the no inputs, how can a prover, okay, how can you convince somebody that a graph does not have a Hamiltonian circuit? So if you think about it for a while, you'll see that this is actually a very difficult thing. Supposing you say that this graph does not have a Hamiltonian circuit, by some way or method or whatever you know this, how do you convince somebody else that it does not have a Hamiltonian circuit? It seems to be an extremely difficult thing. The only way it looks like is if the other person, with or without your help, looks at all possible, collections of edges, let's say, and then sees whether these collections, let's say all edges of psi, take n edges, where n is the number of vertices in the graph, take all possible subsets of n edges and check whether they form a Hamiltonian circuit. Now, this could take a take a long time. Okay, the time taken to go through do this exhaustive checking is certainly not may certainly not be polynomial in the input size. Okay, so and to date nobody knows of anything better. Okay, so for at least for HC, and in fact for many of these problems that we will look at, it looks like the yes inputs behave differently from the no inputs. When the answer is yes, there is an easy proof by which you can convince the other person that it's a yes input. The no inputs seem to behave very differently. Okay, for the class NP, all we require is that when the answer is yes, there should be an easy way to convince somebody else that in fact it is a yes input. Okay, so how do you prove that something is an NP? We've seen two examples, but let's just sort of note this down. So to prove something is in NP, you need to do two things. You have to say to prove that a problem is in NP, you have to do the following things. You have to say the proof that the prover sends to the verifier, and then how does the verifier check? Okay, so these are the two things that you need to send. This proof, by the way, is only for yes inputs. Okay, for yes inputs, there you must say what is the proof given any yes input. What is the proof that the prover sends to the verifier? And once the verifier receives this and he looks at the input, the verifier you should say how the verifier checks, how the verifier is convinced by looking at this proof and the input that the input is in fact a yes input. Okay, and for the Hamiltonian circuit case and for composites, for the problem composites, we specified both. Okay, in the composites case, for instance, the prover sends the factorization and the verifier just multiplies the two of them and checks whether it's equal to the input. Okay, so this we have in fact now defined the class NP. We will see many other examples. In fact, I would encourage you to look at problems that you have previously come across, at least the decision problems, and try and see whether some of these fit into the class NP. Okay. So one importance of this class NP, why define this class NP at all? Well, a large number of problems which occur in real life fall into this class NP. In the following sense, I mean, if you look at problems in real life, they, most of them, you do not want problems with a yes/no answer. Okay, the answer is usually many bits, but these problems can be transformed into a problem which is not much easier. In fact, as hard as the original problem, where the answer is 1 bit. Okay, and when one looks at these versions of problems that you get in real life, very often they turn out to be in NP. That's why this class is very important, because a large number of problems that that you will encounter and that people have been encountering in real life, they all fall into this class NP. Define well, yet another problem, but this is a sort of central problem that we'll work around with. Okay, so this will be a problem in NP, and it will be the central problem. Okay, you would have seen something like this in many of your previous courses in computer science. If you have done logic, you would have seen something like this. You would have seen this Boolean circuits, etc., etc. So many of these concepts that we'll deal with and will define should not be new to you. Okay. Anyway, I'll define the problem. The problem is this. Okay, I need to make a few definitions before I get on with the problem. Okay. Yeah. So a Boolean variable is a variable which takes values in the set yes, no. Okay, it takes two values, yes or no. Okay, now if x is a Boolean variable, then x bar is a negation, is called a negation, is called its negation, and if x is yeah, so we would in fact maybe yes or no will also sort of alternate between true and false, okay, instead of yes and no. Okay, essentially this there are two values, yes, no, true, false, or 1, 0. Okay. So, and if let us say x is true, then x bar is false, and if x is false, then x bar is true. Okay. And x bar is called the negation. Okay. Some people also use tilde x is also used instead of x bar. Okay, so a literal is either a Boolean variable or its negation. So both x and x bar are literals. Okay. A clause is an OR. Okay, I have to define what OR is of literals. Okay, so OR is actually the usual logical OR. For example, I mean, here's an example of a clause x1 or x2 bar or x3 bar or xt. Okay, so here's an example. So the symbol is OR. Okay. So clause is just an OR of literals, and this clause evaluates to either true or false depending on the values that these variables get. Okay. If any one of them evaluates to true, then the clause evaluates to true. Otherwise, it evaluates to false. Okay. For instance, if x1 is true, the clause is true. If x2 bar is true, then it's true, and so on. Any one of them evaluates to true, it's true. It's false if all of them are false, which means x1 should be false, x2 bar should be false, okay, which means x2 should be true, x3 bar should be false, x3 should be true, and xt should be false. Okay, all of them are false, then it's false, otherwise it's true. Okay, let's let me write this. So it's false if all literals are false, otherwise true. Okay, you could have said it's false if and only if all literals are false. Okay, this is the usual OR. And is coming up right now. Okay, so a Boolean formula in CNF is an AND of clauses. Okay, so I have C1 and C2 and C3 and so on, and CK. Okay, each of these is a clause. Okay, this symbol is AND. Okay, which is again the usual symbol that you use in logic. Okay, so this is another definition. So a Boolean formula in CNF is an AND of clauses. Each of them is a clause, C1, C2 and CK, and C1 and C2 and C3 and so on up to CK. This I'll call a Boolean formula in CNF. CNF stands for conjunctive normal form. Okay, so each of these clauses, remember, is an OR of literals. Okay, so this is an AND of ORs, and so it's called a called the conjunctive normal form. Okay, so I just have to tell you the logical behavior of AND, which is again the usual thing. This formula is true, evaluates to true if every clause evaluates to true, okay. Otherwise it evaluates to false. So maybe I can just write if and only if. This formula evaluates to true if and only if every clause evaluates to true. If any one of those clauses is false, then this formula is evaluates to false. Okay. So what do I mean by evaluates to false? It means when you give values to these variables, okay, then if it's a variable, it evaluates to true. If it's the negation, that evaluates to false. Then you check each clause whether it evaluates to true or not. That you check a clause evaluates to true if any one of those literals evaluates to true. Okay, and then you look at this formula. You look at this collection of clauses, and this evaluates to true if all clauses evaluate to true. Okay, of course. These are special Boolean formulae which we call are in CNF, which is you have ands outside and you have ors inside. Okay. Of course, you can form general Boolean formulae which use ands or ors and nots in any kind of way you like. But these are the only Boolean formulae that we are interested in. Okay. And one can show, we will not do it, but one can show that every Boolean formula, take any Boolean formula, that can be written equivalently in CNF. Okay. Okay. I need one more definition, then we are ready to roll. So a Boolean formula in CNF is said to be satisfiable if there exists an assignment to the variables. An assignment assigns the value either true or false to each variable. Okay, there is an assignment to the variables such that the formula evaluates to true. Okay, there is some way of assigning values to these variables. Each of these variables, there is a way to assign values of either true or false, so that when you evaluate the Boolean formula, okay, it evaluates to true. In this case, you call the Boolean formula satisfiable. If not, you say that it's not satisfiable. Okay, so clearly there are Boolean formulae which are in CNF which are satisfiable and which are not satisfiable. Okay. For instance, x and x bar, if I take one clause to be just x and another clause to be just x bar, then there is no way you can satisfy this formula. Okay. Whatever value you give to x, the formula always evaluates to false. Okay, so we are ready to define our next problem that we will study. It's called SAT, not to be confused with exams. SAT stands for satisfiability. Okay, so the input is a Boolean formula in CNF. Okay, and the question is, okay, let me call this Boolean formula something, f is f satisfiable? Okay, this is the question. Okay, so now let's observe that SAT is in NP. Okay, so SAT is in NP. Why is this? Well, it is a decision problem. Okay, and suppose the answer is yes, so we have to only focus on yes inputs. Okay, so the prover says yes, it is satisfiable. Then how can the verifier be convinced that a given formula is indeed satisfiable? Okay, so what does the prover give the verifier so that the verifier can look at this advice that the prover has given him, look at the input formula, and be completely convinced that yes, the formula is indeed satisfiable? Well, I hope most of you have answered this question by now. The proof that the prover gives is just a satisfying assignment. Okay, so the proof is an assignment to the variables. Okay, the verifier uses this assignment and checks that the formula evaluates to true. Okay, the verifier uses this assignment and he checks that the formula evaluates to true. So given an assignment, you should be able to convince yourself that it is easy to check what the value of the formula is. Okay, you just plug in the values into for each variable. Now check whether each of these clauses are true. Okay, if all clauses are true, then you are through. Okay, the formula is satisfiable. Okay, so if it's a yes input, there is a proof that the prover can give verifier, using which the verifier can easily check that the formula is in fact true. Okay, so SAT is in NP. So what's the big deal? Yet another problem in NP. Okay, yeah, it's yet another problem in NP, but this, as we shall see in a minute, is a very special problem in NP. Okay, yeah. So the thing that makes SAT very special is the following theorem of Cook. Okay, Cook is Stephen Cook. Okay, it's the name of a person, Stephen Cook, and yeah, there is no relationship to Tarla Dalal. Okay, so this theorem says if SAT has an efficient algorithm, then so does every other problem in NP. Okay, let's stare at this for a time, for a minute. Okay, so this is among the most important theorems in computer science. So let's make sure that we understand this. Okay, by efficient I mean polynomial time. Okay, efficient means polynomial time. This says that if there is a polynomial time algorithm for SAT, then there is a polynomial time algorithm for every other problem in NP. Okay, so to solve any other problem in NP, it suffices to just solve SAT. I mean, remember that NP includes things like factoring. Okay, it also includes Hamiltonian cycle, matching, etc., etc., etc. Okay, a large number of problems that we have seen so far, in fact, is in this class NP. And this theorem says that if SAT has an efficient algorithm, so does every other problem in NP. We have proved statements of which are sort of similar. We have proved, I mean, this is the notion of reduction. So we showed that if HP has an efficient algorithm, we showed that this means that HC has an efficient algorithm. Okay, we have done this. Now, and this was not easy. Okay, we took a little bit of time and effort to do something which is as sort of well specified as this. Both these problems are very well specified. We knew where we are going. Look at this statement. Here, this says SAT has an efficient algorithm, implies every problem in NP has an efficient algorithm. Okay, this is not just one problem somewhere. It's not Hamiltonian cycle, Hamiltonian path, what have you. It says every problem in NP has an efficient algorithm. So I hope you appreciate the power of this statement. Okay. And this theorem has changed the shape of computer science. So there are two ways of sort of reading this statement. One is to say that if you can solve SAT, then you can solve everything else. So concentrate all your sort of attention on SAT. That's one way to do it. A lot of people have tried, and they have not been able to find an efficient solution for SAT. So the other way to sort of do this, look at this statement, is SAT is among the hardest problems in NP. Here is a class NP, and SAT is among the hardest problems, in the sense that if you can solve SAT, everything else follows. Okay, so it's among the hardest problems in NP. Okay, so SAT is one of the hardest problems. Are there other problems in NP which are as hard, of which I can make a statement which is similar? That if this problem is as hard, I can solve this problem in NP, then I can solve every other problem in NP. Can I make this statement of other problems? And how easy or difficult is it to prove these statements? Fortunately, with Cook's theorem in hand, there are, in fact, let me sort of say that there are such problems in NP, and with Cook's theorem in hand, proving that these problems are among the hardest problems in NP becomes a bit simpler. Okay, I mean, how does one go about doing it? So here is one way. Okay, so I take a problem, let's say some problem pi. Okay, so what I'll do is this: if there is an efficient algorithm for pi, then there is an efficient algorithm for SAT. Supposing I can prove something like this. Now this is something we have been doing, and it looks like we are capable of doing such things. Okay, we have done it for, instead of pi and SAT, we have done we have taken HP, HC. Okay, and well, matching, we have seen some examples from matching where we have taken two algorithms, two problems like this, and we have shown that if there is an algorithm for a problem, then there is another algorithm. Okay, essentially we use a subroutine for pi and we construct an algorithm for SAT. Okay, so something like this we can do. But now let's see what this gives us. Now here's the other sort of implication that I would like to use. Cook's theorem says that if there is an efficient algorithm for SAT, there is an efficient algorithm for every problem in NP. Okay, there is and efficient for all of NP, which means all problems in NP. Okay, so let's just put these two things together. If there is an efficient algorithm for pi, there is one for SAT, and if there is one for SAT, there is an efficient algorithm for all of NP. This follows from Cook, and this result we will have to cook up. Okay, so this is up to us to prove. So to prove that pi is among the hardest problems in NP, all I need to do is prove that if there is an efficient algorithm for pi, there is an efficient algorithm for SAT. Okay, and once I do this, using this implication, I am down to proving that there is an efficient algorithm for all of NP. Okay, so this would sort of identify pi as among the hardest problems in NP. Okay, so let's identify. So our goal for the next few lectures, few hours, okay, will be to identify more and more problems in NP, so, which are among the hardest, in the sense that if you solve these, then you can solve every other problem in NP. Okay. So here's the first one. I need to make a definition. So a clique in a graph G is a subset of V such that the subset, let's say U of V, says that when I look at any two vertices in U, there must be an edge between them. Okay, so you look at a graph, you look at a small subset of the vertex set, and in this subset, when I look at the vertices, if between any pair of them there is an edge in the graph, then this I will call a clique. Okay, the subset U says that for every U1, U2 in U, U1, U2 must be an edge in G. Okay, must be an edge in G, which means if I restrict myself to U, I must get the complete graph. Every edge must be present. Okay, let's take an example. Okay, let's take this example. A, B, C, D, E, G. Let me add this. Okay, in this example, A, B, C, D is a clique. Okay, if I look at these four vertices, every possible edge is present. I cannot replace C with E. Okay, A, B, D, and E is not a clique because E is not adjacent to A and D. Okay, if I just take A, B, D, that's a clique. If I take just D, C, and G, that's also a clique. Okay, this is a clique of size 3. This is a clique of size 4. Okay, it's a subset of the vertex set such that if I take any two vertices, there is an edge between any pair of them. Problem is this. So this is the search version. The input is a graph G. Okay, the output, find a clique of maximum size. Okay, find a subset, find the largest subset you can, so that when I look at this subset of vertices, it forms a clique. Okay. So in this graph, for instance, the largest clique that you can find is of size 4, which is this ABCD. That's the largest clique in this graph. So the search version is this. Remember, we are trying to identify problems in NP. This is not even a decision problem. Okay, you want the vertices in a largest clique, right? So we need to look at what we'll do is we'll define a problem which is very similar to this, okay, which will be a decision problem, and then we'll focus on that. Okay, so the decision version is this: clique the input is a graph G and a positive integer k. You will see how k creeps in, or why k creeps in a minute. The question is, or does G have a clique of size k? Okay, this is the question that we look at. So let's focus on these two problems. Okay. Now the second problem, it's a decision problem. In the sense, the answer is either yes or no. Okay, so that's fine. Now, if you can solve the search problem, okay, if there's an algorithm to solve the search problem, clearly there is an algorithm to solve the decision problem. Just find a clique and find its size. If the size is k or larger, then you are done. The graph does have a clique of size k. On the other hand, suppose you have an algorithm for this. How do you find? Can you solve the search problem? Well, the answer is yes, and the construction is very similar to what we have done earlier. So what you do is first find the size of the largest clique. Okay, you can do a binary search on k. Feed in the graph with various values of k. Okay, and essentially you want to find the largest value. I mean, if the graph has an edge, if k is 2, the answer is yes, right? So find the largest k for which this is true, and this you can do by binary search. You can even go sequentially and do this. K equals 1, 2, 3, 4, 5, 6. Stop as soon as it answers no. The previous one was the largest clique, size of the largest clique in the graph. Okay. Once you have found the size, let me write this. So first, so hint. Well, I'm going to give you more than a hint. Hint is first design an algorithm to find largest cliques size, okay, or size of the largest clique. Okay. Once you do this, now you use this to solve this. Okay. What you do is look at the vertices one by one. Okay. Throw away a vertex and ask, does this graph, what is the size of the largest clique in this graph? If it is k, I mean if it is the same as that for G. Okay. Okay, so let me just backtrack a little bit. So first you feed this graph G and find the size of the largest clique. Let's say k0. Okay. So k0 is size of the largest clique in G. Okay. Now I remove a vertex and ask whether there is a clique of size k0 in this graph. If yes, I throw the vertex away. If no, I retain the vertex. I go through all vertices, and at the end I would have thrown away every vertex except k0 vertices, and these will form a clique. Okay. So this is very similar to finding edges in the Hamiltonian cycle, which we did earlier. Okay. Only here we throw away vertices instead of edges. Okay. So I would I'll strongly encourage you to follow through these steps which I have just said, and make sure that you can do this. Okay, given an algorithm that that solves the decision version of the clique problem, describe an algorithm that solves the search version of the clique problem. Okay. Okay, so now, so the decision version seems to be as hard as the search version of the clique, and from now on we'll focus on the decision version. Can we solve the decision version or not? In fact, our goal is to show that the decision version is among the hardest problems in NP. Okay, just like SAT, which means if there is an efficient algorithm to solve the decision version of this problem, there is an efficient algorithm to solve all problems in NP. Okay.